Hello, I'm Michael Firth in Product Marketing at Texas Instruments, and today I'm going to discuss the motor signal chain. In terms of an agenda, we'll focus in on the motor driver basics, primarily focusing in on the H-bridge, the associated protection circuits, their various control interfaces, and towards the end we'll spend a bit of time covering the current sense amps, ADCs, and isolation devices found in a typical motor drive system. We've got a functional diagram here of a motor control system, with the left-hand side showing the system controller, and in this diagram we're showing it communicating with the motor controller via a bus such as a CAN or RS-485. You've got the gate driver and the H-bridge. Now the definition of a motor driver can vary somewhat depending upon the part you're dealing with. Typically at a minimum it includes that gate driver, the H-bridges, and the associated protection circuitry. But it may also include a fair amount of control logic or an actual controller integrated into the motor driver. You can also have the controller standalone, such as a C2000, MSP430, or ARM-based controller. It just depends upon the device that you're dealing with, how much of that control has been integrated into the actual motor driver. Now these systems typically have a couple different levels of feedback. The red here is showing the torque or commutation loop. When I talk about commutation, what I mean there is that's how, in a sensorless application, how you're actually controlling the motor itself, how you're spinning the motor. The torque is related to the current, so it's measuring the current. And the way you do that is you measure a voltage across that sense resistor. The sense resistors are typically quite low in resistance. The current sense amp sends the reading to the ADC, who digitizes it, and you pass it on to the controller. Another feedback loop is the speed loop, and that typically involves an optical encoder or a Hall sensor. Now the outputs on these encoder and sensors are digital, so you don't need any type of current sense amp or ADC. You can just run that directly into the controller. It's a digital output. And finally, position loops are quite common. Those typically involve either a resolver or an optical encoder. If it's a resolver, the output on a resolver is analog. It's a sine or cosine wave, actually both. And you need an ADC to digitize that, feed that into the controller. If it's an optical encoder, that's just a digital output, and you can deliver that straight to the controller. These motor systems also typically require isolation circuits, especially at the high voltages when you're in the 300, 400, 500 volt range. That gate driver and H-bridge section is at a very high voltage, and you need to protect that from the low voltage control section, so isolation is required. You can also need isolation to increase the range of those communication protocols, those bus, the CAN, RS-485, especially in these noisy industrial environments. The isolation devices help extend that range by breaking the ground loops and decreasing the noise on the line. Okay, let's delve into the actual motor driver itself. At the heart of the motor driver, you've got the H-bridge. And just like you find in audio and in power supplies, the H-bridge is chosen for the high efficiency. You can use a linear amplifier to drive these motors, but you're not going to get the same level of efficiency. In addition to the actual H-bridge, you've got the high side and low side gate driver circuitry. You've got thermal protection, overcurrent protection, and in many instances you've got current regulation built into that motor driver. So the first question is, what is a gate driver and why is it needed? So the gate driver is the circuitry that actually turns on and off the power MOSFETs. It's got to be able to control the timing of when those MOSFETs are turned on and off, that high side and that low side. You never want the high side and low side turned on at the same time. Otherwise you're going to have a condition called shoot-through, where you've basically shorted that battery directly to ground, and that's going to destroy the device. So the gate driver is responsible for turning those FETs on and off in such a way that you have maximum signal linearity and maximum efficiency, but those devices are also protected by inserting a small amount of off time called dead time to prevent that shoot-through. So the gate driver circuitry is very important in terms of the overall performance of your MOSFET. Now when looking at the FETs themselves, one of the first distinctions you'll see is, are they NMOS or PMOS FETs? The advantage of the N-MOSFET, at least from a die area, is that it's much smaller. This is especially true at the higher voltages. At some of the lower voltage nodes, 5 volt and below, they can actually become fairly comparable in terms of die area and cost. But at the higher voltages, for sure, the NMOS is much smaller, which equates to lower die cost. The drawback of an NMOS is that you need the gate supply voltage to be 10 to 15 volts higher than the source voltage. In a PMOS, you don't need that. You don't need any type of extra voltage to turn the PMOS on or off. So then the challenge is providing that high side supply for the NMOS. And typically you provide that with an on-chip charge pump or external bootstrap capacitors. Another characteristic to look at on the MOSFETs are the body diodes of the FETs themselves. These are inherently with every FET. They're part of the FET structure, and they've got to be robust enough to handle the recirculation currents that we'll talk about shortly, and also be able to handle short circuits. If your body diodes are not robust enough, you're going to need to add external Schottkys, and that's going to add cost, added components, and board space. The primary characteristic of a MOSFET is its RDS(on), and that is the resistance of the FET when it's turned on and conducting. That is the dominant factor in the overall efficiency of the motor driver. Now, switching losses, the PWM frequency, how quickly you're turning on and off those transistors, also are a major factor, but they pale in comparison to the RDS(on). That's the dominating factor of how efficient that MOSFET is. RDS(on) increases with temperature. Typically, in the data sheets, you're going to see a room temperature RDS(on) measurement, and you may or may not see an elevated temperature RDS(on) measurement. But just be aware that as that device is operating, the die is going to heat up, and therefore your RDS(on) is going to go up. And it's not a trivial amount. If you look at the graph in the top right-hand side, you can see that around 80 to 90 degrees, the RDS(on) is increased 20 to 25% from room temperature, so it's a significant factor. Now, another thing you've got to look at when you look at MOSFETs or motor drivers, they're rated in terms of a continuous current and a peak current typically. What you'll find out is many times the maximum continuous current is limited by the thermal performance of the device. Meaning, electrically, so the supply voltage and the load that it's driving, the amount of current you're outputting, electrically the motor driver can easily handle that. But as that current is flowing through those FETs, that RDS(on) is a little resistor, it's heating up. And the die temperature is going to get excessive, and an over temperature event is going to occur. So one of the keys to good motor driver design is how do you thermally handle that device? Can you efficiently get the heat out of the device? If you can guarantee you can support the continuous current ratings, and depending upon the device, you may even be able to get higher current ratings out of that device if you can thermally get the heat out of it. That's not the case for every device, but many devices are thermally limited. The challenge is how to get the heat out of it to ensure that you can keep maximum current flowing out of the device. So in terms of the PWM frequency, there's a couple trade-offs here. The first is, in an ideal world, you want to get the PWM frequency out of the audible range. And that's simple enough in terms of the reason you want to do that is if it's in the audible range, you can hear that. And you can see this in some of the legacy motors that are using the switching frequency where they're, say, 15 to 16 kilohertz. You can actually hear the switching frequency of that motor. So if you can get it above the audible range, you're going to cut that noise out. Also, the faster you switch the frequency, the smaller the ripple current, which directly relates to how smooth that motor runs, how quiet that motor runs. That's going to go down. The downside is as you increase the switching frequency, the switching losses start to increase. Therefore, your efficiency does start to go down. So it's somewhat of a trade-off, and the exact switching frequencies many times will just depend upon the application. Okay. Let's take a look now at an actual H-bridge flowing current to turn the motor. In this example here, we've got the H-bridge connected to the supply, but all 4 H-bridges are turned off. As we turn on the high and low side, opposite sides of the leg, current begins to flow. Now through Lenz's law, we know that the current, when current flows through a conductor in a magnetic field, you're going to generate a force. Therefore, that motor is going to start to spin. Now, if you turn on the opposite high and low side FETs, the current will flow in the opposite direction. Therefore, it's a negative current. The force will be opposite, and the motor is going to spin in the opposite direction. And the thing you want to avoid at all costs is shoot through, and that again is where the high side and low side FETs are turned on simultaneously, making a direct short. You're going to blow that driver there. You want to avoid that at all times, and that's where the gate driver circuitry comes in, inserting dead time to ensure that that never occurs. Okay, if we look at a motor, the first thing we got to realize is that it's a very large inductive load, and inductors by definition do not like current to change rapidly on them. So as you're PWMing the voltage or the current to the motor, when the PWM duty cycle is off, you're going to have some recirculation currents. The inductor is not going to allow the current to go to zero. The current's going to continue to flow. And the question is, how do you handle that? There's a couple different options. One is to basically do nothing and let the current basically just freewheel. And what that means is the inductive current is going to flow through the body diodes of those FETs, completely uncontrolled. Or you can use a synchronous decay method where you actively turn on the FETs in certain ways to control how that recirculation current flows. And there's some definite advantages to using a synchronous decay in terms of much lower power dissipation and also much better control over that current. This slide here is showing how the FETs are configured in a synchronous versus asynchronous decay mode. And if we start with the first H bridge, that's normal operation. The high and low side FETs are turned on, the current is flowing, motor is spinning, everybody's happy. In an asynchronous decay, you've turned all 4 FETs off, but that current with the inductive load has still got to flow. So the back EMF is going to generate current that's going to flow through the body diodes there, completely uncontrolled. Now, one of the things to note there is in terms of power loss, your power loss is going to equate to the current flowing through the bridge times 2 diode voltage drops. Now in synchronous decay, instead of just letting the current freewheel, you turn on, for example, the low sides in this example, and you provide a low resistive path for that current to flow. One advantage right off the bat is typically the RDS on is low enough that the power loss in synchronous decay is going to be much lower than the voltage drops across those diodes. So it's going to be more efficient in synchronous decay. So now let's look at some specifics of a motor operation. And one of the decay modes is called slow decay. So in normal operation, again, the motor is spinning, current is flowing with the high and low side being turned on. The next H bridge there shows the dead time, and this is unavoidable. There's a small amount of time always inserted to make sure you don't have any shoot through. During that time, those diodes are going to freewheel, the current's going to freewheel through it, but the dead time's pretty short compared to the overall decay time. If you look at the third H bridge, the slow decay there, you've turned on the 2 low sides, current is recirculating through the low sides, it's a low resistive path. What you get in slow decay is low current ripple. It's going to decay fairly slowly. It's directly proportional to the inductance and the resistance of that system. So the lower the ripple, that equates directly to less motor heating, much smoother and quieter operation. But that slow decay is exactly that, it's slow. And it may not decay fast enough for a proper control of the motor in some situations. Now if we look at another decay method called fast decay, again we've got normal operation here where the high side and low side are conducting. Motor spinning, everybody's happy. The dead time we talked about. Now instead of turning the 2 low sides on, we actually turn on the high side and low side, and we use the battery to help drive that current down very quickly. So it's seeing that supply voltage, or it's fighting that supply voltage. So the current decays very quickly. Now when it decays quickly, you're going to have much higher ripple current, and that equates to hotter motor operation, more torque ripple, which basically is louder operation. The operation is not near as smooth, especially compared to slow decay. So there's some disadvantages to fast decay, but when the winding current is decreasing, fast decay typically provides much better control over the current than slow decay, and that's really important in stepper applications, and I'll show that in just a second. Okay, on this slide, the red sine wave represents the current that is being supplied to a stepper motor when it's microstepping. Sine wave commutation is one of the best ways to drive a stepper in microstepping in terms of smoothness and quietness of the motor. Now, the thing to take a look at is on the first portion of that sine wave cycle, as the current is increasing, it's using slow decay. Now this mode that I'm talking about right here is called mixed decay, which is a combination of slow decay and fast decay. So as the winding current is increasing, you use slow decay, and we talked about the advantages of that, which are basically less torque ripple, smoother operation. But as the current starts to decrease, due to the inductive load of the motor, if you were to use slow decay, you may not be able to reproduce that control signal, that sine wave control signal, accurately at the motor. So the inductance would start to affect it, and you'd get some distortion in that control signal, and you'd basically start to get very poor performance out of the motor. So by switching to a fast decay or a mixed decay as the current decreases, you get a lot better control over that current. Therefore, you're going to get much smoother operation. Okay, let's talk a little bit about braking. You'll see braking referenced in brushed and brushless motors quite often. And if you take a look at the first H-bridge, we've got the high side and low side FETs on, so current is flowing through the motor. But the thing to remember is as the motor is spinning, it's creating a back EMF. So it's in that magnetic field as the current is flowing, it's creating a voltage to oppose that current, oppose that motion, if you will. So that back EMF voltage is always present, but it's less than the supply voltage, the battery voltage. So therefore the motor continues to spin, it's just not drawing as much current. That back EMF is fighting it. Now what happens when you want to brake the motor, when you want to slow it down, stop it immediately, or as fast as you can, one way is to leverage that back EMF. And one of the ways to do that is you can turn the two low sides on. And what the low sides do is it allows that back EMF, you're basically shorting those motor leads, and you're allowing that back EMF, that voltage, to drive a current in the opposite direction of the supply. So that opposite current is going to generate an opposite force, and that force is going to fight to slow that motor. You're going to brake that motor very, very quickly. You're going to slow it down very quickly. So that's braking, basically allowing the back EMF to stop the motor very quickly for you. Now another common mode is coasting, and in this mode, instead of shorting the back EMF, you actually open it up. So again, we've got normal operation, currents flowing, you've got the back EMF, you've got the supply voltage. When you put it in coast mode, you basically turn off or tri-state all four of those FETs. So you've opened the motor circuit. The back EMF now has nowhere to flow. So the only thing that's going to slow that motor down is basically the kinetic friction of the rotation itself. The bearings, the various mechanical aspects of that motor are going to slowly, the friction is going to slowly bring that motor to a halt, to a slow stop. And that's what's called coasting. Okay, let's talk a little bit now about the protection circuits that you find in a motor driver. So there's a number of different protection circuits. The first and probably the most important is the overcurrent protection. Some motor drivers, as we mentioned, also have a current regulation feature. Over temperature is very important, under voltage protection, and cross conduction protection. Okay, so probably the most important protection is overcurrent protection. You've got pretty high supply voltages. These motors inherently have low winding resistance, and you're always worried about the potential for shorts, some type of short to ground, to power, or across the windings. So you want your motor driver to be protected. The trick there is to have a protection circuitry that can trigger fast enough to prevent any type of damage, but also be intelligent enough to not trip on false trips. The body diodes also have got to be robust enough to handle the shorts. You don't want the body diodes breaking down and the device being destroyed because the body diodes can't handle it. So typically the motor drivers have the on-chip overcurrent protection built in. They are monitoring each individual FET, so you're fully protected against these shorts. When an overcurrent event occurs, the fault can either be latched or auto recovery. So if it's latched, the device is going to tri-state, it's going to shut down, and the system controller is going to have to come in and reset it. If it's auto recovery, it'll wait a preset amount of time and it'll try and resume operation. If the short is still there, it'll just continue to cycle through that cycle until that short's removed. So the nice thing about that is if the short was some type of transient or just something that wasn't really permanent, once that's removed, device operation will return. Now some devices also have a fault pin, and in the event of an overcurrent trip, it will notify the system controller that the overcurrent trip has occurred. Okay, current regulation. So current regulation basically sets a limit for the maximum current that motor driver is going to output. You can program that in a number of ways. And the way it limits that current is it starts to limit the duty cycle of the PWM, of the switching frequency. So as it limits the duty cycle, that duty cycle is directly proportional to the voltage. It's basically decreasing the voltage. So as if your motor was in a set of conditions that it were going to require current above the current limit, it would start to, on a cycle-by-cycle basis, start to limit the PWM voltage. And that's what you're seeing in the yellow, where if that had no current limit protection, the PWM cycle would be longer and the output current would be quite a bit higher. But with the current limit in place, it immediately limits the duty cycle, therefore limits the voltage, therefore limits the current. Now this is different than your overcurrent protection, where the overcurrent protection uses a different mechanism, shuts the device down and protects it. This is just to limit the maximum output current. Now, current regulation is very important for stepper motors. Stepper motors are almost always designed to be driven with a motor driver that has regulated current. You've got very low resistance windings, and a stepper motor doesn't have the same level of back EMF that a DC motor does. So very low resistant winding, it's going to draw a lot of current. You've got to go in and manually limit that current. DC motors also require current regulation during startup and stall conditions. And I'll show a slide here in a second that at startup, you don't have any back EMF pushing back. The winding resistance is very low. You're going to get a lot of inrush current. So you need a method to limit that current during startup and stall. So this slide here shows exactly that. If you look at the left bottom, the green line is a trace of the current draw when you start up a DC motor. That current reaches over 14 amps, but it quickly comes down as the motor starts to spin. It starts to generate the back EMF. The current draw starts to come down. But you don't want to have to design your power supply system to handle 14 amps, and you don't want to have to design your motor driver to handle 14 amps when the actual continuous current is much, much smaller. That's just overkill. So the solution there is the current regulation. And on the right-hand side, the blue line shows the current regulation in action, where it's limiting that inrush current at the first, Once again, the back EMF gets established, the current draw comes down, and you've got normal operation. Okay, so thermal shutdown. Typically, multiple sensors are placed in the power FET to continuously monitor the temperature of the die. And when the die hits a preset temperature, and it's somewhat dependent upon the process and the design that the device was built in, it's going to trip, it's going to shut down and self-protect. And that typically tri-states those H bridges. Now that fault can be, once again, latched or auto recovery. You've also got some devices that have the fault pin that'll notify the system controller that an overtemp condition has occurred. And some devices actually have a two-stage thermal protection where they'll provide a warning at a lower temperature than the trip temperature. So for example, some of the DRV83 family have two-stage protection where they will send a warning to the microcontroller at 125 degrees C, saying, hey, we're getting pretty hot, we're getting close to the trip point. And once the 150 degrees is passed, it'll go into thermal shutdown and protect the device. So a two-stage thermal protection. Finally, you've got undervoltage and cross-conduction protection. The undervoltage protection is really meant to protect you from ever losing control of those gates. And if you think about that in terms of the potential for a shoot-through, or you've just got high voltage there, you don't ever want to lose control of those gates in the event of you got a brownout condition or the supply voltage to the driver itself was going low. You don't want those gate drivers to lose control, so it'll monitor the voltage levels. If they become too low, it's going to shut the device down and just eliminate any possibility of losing control over those H bridges, those output FETs. Now, cross-conduction protection we talked about, that's really tied to the gate driver. That's ensuring that the high side and low side are never turned on simultaneously. And we mentioned earlier that this is accomplished by inserting a small amount of off time where the FETs are off. We call this the dead time. It's inserted right after turning the high side off, but before turning the opposite low side on, or the actual same low side on. Now there's a trade-off there. The longer the dead time, the safer, more robust the operation. You just got more and more guard band. But as you insert more and more dead time, the linearity and efficiency start to get worse. So there's a trade-off there. You've got to make the right choice there in terms of safe operation versus linearity and efficiency. But that's all handled by the gate driver. So let's take a look at some of the control interfaces, how you control and drive these motor drivers. So a number of control interfaces have developed over the time. The more common ones are listed here. We've got a parallel, or many times you hear this as a phase enable. It's a very simple two-wire control interface that's got a phase and enable pin that controls direction and speed. You've got an indexer interface. Those are specific to steppers, which have a step and direction signal. Indexers also have on-chip indexers, which basically calculate the current and the phase to either handle the stepping, full stepping, or micro stepping. That's built into the device. There's no need from an external processor point of view to support that. It's all on chip. You've also got N1, N2 type interfaces. These provide independent half-bridge control. They're somewhat of a legacy interface. You'll see PWM interfaces referenced. Now those can be very similar to the N1, N2, or they can be different. It just depends upon the H-bridge logic output states. It's also common to see PWMs control individual FETs, so a high side or low side, control a half bridge, or even control a full bridge. So there's some variety in those PWM interfaces. And finally, you've got a serial interface, and those are great for controlling multiple motors on a single low-pin bus. So for example, there's some drivers in our portfolio that you can hook up to 9 drivers on an I2C control bus. If we look at that phase enable interface, there's 2 different ways to control it. Same exact interface, but 2 different ways you can configure or control it. The first is by PWMing the enable pin. So the phase enable, simple 2-wire control interface. One is the enable pin, One is the phase. The enable controls the speed, and the phase controls the direction. So by PWMing the enable pin, you are directly controlling the amount of voltage that the motor is seeing. And the speed of a motor is directly proportional to the voltage. So as you PWM that duty cycle from 0 to 100%, you're increasing the voltage, you're directly controlling the speed of that motor. So now if we look at the phase enable interface, but we want to control the speed and direction via PWMing the phase signal. So same exact interface, it's just now you use the enable pin to either just turn on or off the motor, and that phase pin, by PWMing that phase pin, you control both the speed and the direction. And that's really nice because now you've got a single control signal to control that motor, both speed and direction. The way you accomplish that is with the duty cycle of that PWM. If it's under 50%, it's going to rotate counterclockwise and the speed is proportional to the duty cycle. If it's over 50%, you're going to rotate clockwise. So again, single pin direction and speed are controlled. Now the disadvantage is if you've lost the resolution. You basically split in two, cut in half the resolution of the speed versus the phase enable where you're PWMing the enable pin. Okay, so in terms of the PWM versus the N1, N2 interface, the key here is they can be identical or they can be different. They're very similar in nature. You need to take a look at the H-bridge logic tables to see if they're identical or how they differ. And the example here on the PWM, with the 0, input, your output 1 and output 2 of the two half bridges are both low. So it directly corresponds to the inputs. But in this example on the N1, N2, the 0 actually tri-states the out 1 and out 2. Now, this truth table can actually vary from one N1, N2 device to another, so it's not set in stone. You need to check each one of them. But in this particular example, you're tri-stating the outputs. And the reason you want to tri-state the outputs, if you remember when we talked about coast mode, that's how you put the motor into coast. Now, with the PWM interface, you can still coast it, but you're gonna put it in a coast mode in a different manner, not by the PWM signals, maybe through a reset signal or some other signal. Okay, let's take a look at some actual parts. So here we have the DRV 8332. This is a 3-phase high current PWM motor driver, highly integrated. So all the gate driver, protection circuitry, everything we talked about, except for actually the current regulation, is integrated into this DRV 8332. Now in terms of the control interface, it's a PWM control interface, and you're relying pretty heavily on a controller to drive this device. There's not much logic built into this device in terms of control. So when we talked at the very first slide about the functional diagram, this really requires an external controller. The controller is what's driving this device. In this example, we've got it hooked up to a C2000. From a voltage level, it'll support from 0 to 52 volts, 8 amps continuous, 13 amps peak. The peak currents, and this is very common in motor drivers, you're going to see two different current levels. And you need to be careful, make sure that you're not just reading the peak current, you need to look at the current continuous. The peak is exactly that. It's meant to, the device can withstand that level of current for very short intervals, say, on the milliseconds or microseconds, just depending upon the device. That could be your peak currents during startup or stall and so forth. But continuous, 8 amps continuous, these are very efficient devices, up to 97% efficient. That's 110 milliohm FETs, so very low RDS on. The power FETs in this device are very robust. No external shotkeys are needed. I mentioned the 3 independent half bridges. The reset pin is how you tri-state the half bridges in this 8332. In terms of protection, it's got the cycle-by-cycle overcurrent. It's not current regulation, it's an overcurrent protection. It'll cycle-by-cycle. That's for the stall and the startup currents. It does have a 2-stage thermal protection, so at 125 degrees that OTW is going to go low, let the controller know that it's getting hot, and it'll shut down and send a fault if you cross 150 degrees. And it does have also the built-in undervoltage protection. So this device here is actually a stepper motor, and you can compare and contrast that to the 8832. It's quite different. The first thing is the current levels are a little bit lower, 1.75 amps continuous, 2.5 peak. Supply range is close, but not quite as high, 8 volts to 45 volts. But if you look at that block diagram, you can see there's quite a bit of logic built into there. There's an on-chip indexer. So this device has a fair amount of control built directly into the driver itself. In terms of the interfacer, this is the index interfacer. You can see here you've got the step and direction pins. That every time the step is pulsed, the stepper is going to advance or retract one position depending upon the polarity on the direction pin. You can set the decay mode. This device, when the winding current's increasing, is in slow decay mode, but when the current is decreasing, you've got a choice here. You can actually pick and tell it to decay in slow mode, fast mode, or a mixed mode, which mixed mode is 75% in, I believe, slow decay, and then 25% in fast decay. In terms of microstepping, you have 3 pins here that'll set the step size, and it'll support up to 32 microsteps. So it's got a built-in indexer and control logic. It's got a lookup table, and it knows all the correct currents and polarity to generate that microstep, 1/32 or even 1/16 or 1/8 or so forth, or even a full stepper. But that's all built in. You don't need any type of external processor. You just need to drive this device. You just need a signal to drive that step and direction. In terms of the current regulation, that's programmable, and you can set that with the reference voltage and also a sense resistor, the value of that sense resistor. Now this current regulation limit sets the maximum current this device is going to output, and when you microstep, it's going to basically be, all the current levels are all going to be relative to this current limit that you set with this reference voltage and this sense resistor. And finally, it does have the fault flag and overcurrent protection notification. So in the event of a fault, it's going to notify an upstream system controller. Okay, let's spend a little time now talking about some of the other motor signal chain parts, the current sense amps, ADCs, and the isolation. So current sense amps are primarily needed when you're running sensorless in a 3-phase brushless motor. You measure the current in anywhere from 1 to 3 of the legs, and you use those current readings to set the commutation. So the commutation, again, is how do you control that motor? How do you keep that motor spinning? That's when you're commutating it. And the critical performance requirements on these sense amps is they've got to have a good common mode output range. You're going to need a high slew rate, good gain bandwidth, low DC offset, and good common mode rejection. And the way these amps are working is, in each one of those legs, you are taking a differential voltage measurement across that sense resistor. And those sense resistors are very, very small impedance, or resistance, I should say. So you're going to generate a very, very low voltage, differential voltage, on a leg that's actually flowing, very high current. So it's very critical that that these devices have very good performance, because you're going to commutate based off of this reading. So you need to get that reading correct. It's got to be accurate. With respect to the analog to digital converters, the critical performance requirements here, first of all, almost in all applications, you need at least 2 simultaneous samples. When you use a resolver, so you're doing position feedback, that resolver is an analog output. It basically has a sine and cosine component to it. So you're going to need 2 simultaneous readings to basically control the position. When you look at the current sense resistors, it's typically 2, sometimes 3, sometimes 1, but many times it's 2 current sense resistors. So you've got to measure those currents in those legs simultaneously, both the 2 legs at exactly the same time, in order to commutate correctly. terms of the resolution, what we've seen is typically anywhere from 10 to 12 bits is usually pretty good. Of course, the greater the number of bits, the more accurate, the smoother the control you're going to get, but it does become somewhat of a trade-off in terms of cost versus resolution. So you move to a 14 or 16 bit, you're going to get better performance, but it's also going to cost more. You've got to make that trade-off. Is that what your system requires? Finally, the aperture time is also important on these ADCs. So the aperture time is how long does it take for that ADC to actually get a reading. And this is really critical in some of these low-cost implementations where you're using only a single shunt resistor. So you're only taking a reading off of a single, off the basically the bus, all three of them combined, or a single one. Actually, all three of them combined, and you've got to take two readings spaced apart. And in the three legs, as the currents are changing, the time, the window in which to get that measurement can become very small, just depending upon where the motor's at in the commutation. So you've got to be able to quickly get that reading and feed that back in order to commutate properly when you're using just a single sense resistor. If you look at the isolation, there's two primary reasons here to use isolation in a motor system. The first and foremost, I think, is safety. We talked about these high voltages of these motors. They can easily be in the hundreds of volts, where your control is in a 5 volt or 3 volt type plane. So you want to have some isolation, some strong galvanic isolation between those two voltage domains for safety reasons. In addition to the safety aspect, the very noisy industrial environments, as these motors become more and more networked, and you need to control them remotely, they're using CAN buses, EtherCAT, RS-485, and these buses in these noisy environments have range limitations, and you can greatly extend that range or just increase or lessen, I should say, the bit error, improve the performance of those buses by putting some isolation in between the controller and the bus itself. TI's got some really nice devices in this area. The ISO 1050 is actually an integrated CAN transceiver with isolation built in, and again, that will help extend the range, and it does that by breaking the ground loops and just reducing the noise overall. So in terms of additional information, we've got two sources here. You can go to TI's motor control homepage at www.ti.com/motor control. We've got quite a bit of information there, including controllers, the analog motor signal chain, app notes, and so forth. We've also got a forum dedicated to motor drivers where you can go and post questions. That is at e2e.ti.com. You'll see the application section on the left. Just click on that, and the motor control will be an option. Just click on that. You can go there again, post any questions you've got about our parts or general questions. You can also read previous posts and learn quite a bit of what's been going on in the motor world. So with that, I'll bring the presentation to a close. I wanted to thank everyone for taking the time to attend, and I'll open it up for questions.